Welcome to the 2025 GVSU Engineering Senior Project Presentation for Team 9, Roll Forming High Strength Aluminum, sponsored by Katayama Manufacturing. Meet the team. Aiden Longpre, Team Captain, Mechanical Engineering. Jacob Law, Sponsor Point of Contact, Mechanical Engineering. Logan Wiesner, Secretary, Product Design and Manufacturing Engineering. Tim Osipsov, Simulation Lead, Mechanical Engineering. Kyle Shaver, Enforcer, Product Design and Manufacturing Engineering. As the automotive industry continues to push for lighter vehicles to meet fuel efficiency, safety, and emissions targets, there's growing demand for materials that are both lightweight and strong. Many of these automotive parts are produced through a process called roll forming, where thin metal sheets are gradually shaped into a profile by passing it through a series of rollers. High-strength aluminum alloys, like the 6000 and 7000 series, are promising candidates, but their behavior during roll forming isn't fully understood. This presents an opportunity for Katayama, who is working to pioneer the integration of these advanced materials into their processes. The goal of this project was to develop practical, validated guidelines for roll forming high-strength aluminum. First, the team researched material properties and roll forming behavior of a variety of high-strength aluminum alloys. Ultimately, 6061 T6 and 7075 T6 were chosen as the test materials. Understanding the properties of these materials helped the team predict how each alloy would behave during forming and guided simulation and tooling decisions throughout the project. One of the key technologies used in this project was Copra software from Data M. It was used to simulate the roll forming process, optimize roll designs, and perform FEA analysis of the formed parts to predict material behavior and part geometry after forming. Using Copra, the team simulated the roll forming process, inputting estimated values for bend angle per station, bend radius, and other key parameters. The simulation modeled the bending sequence at each station, allowing the team to adjust the roll design as needed. This approach enabled data-driven decisions to refine and optimize the tooling. Based on the initial simulations, material research, and input from industry contacts, final sets of rolls were designed and optimized for testing that fit within the budget. The final roll designs were used to simulate the prototype roll forming process for the chosen materials. The rolls were also manufactured by Roll Form Solutions as prototype roll sets for physical testing. Here are some of the key features of the prototype and forming setup. The hat shape profile allowed the team to evaluate 4 bends in a single part. Edge traps were added to help control material alignment on the rolls. These were also used to precisely adjust roll gap for the material thickness. Finally, a reverse curve overbend was included to allow for overbending while ensuring the rolls would fit together. With the final roll sets manufactured, the team conducted prototype testing using both 6061 T6 and 7075 T6 aluminum. Prototype parts were formed using the 7-pass setup at Roll Form Solutions. Key characteristics like ultimate tensile strength, hardness, and thickness were measured before and after roll forming to evaluate changes caused by the forming process. After forming, the team also assessed longitudinal bow, springback, cracking, and dimensional accuracy. These results were then compared to the simulation outputs to validate the accuracy of the model. For die penetrant testing, no cracks were found in the 6061 T6 samples. However, the 7075 T6 samples showed small hairline cracks at the top flange bend. Cross-section measurements showed springback of about 5 degrees for 6061 T6 and 9 degrees for 7075 T6. Longitudinal bow was similar across both materials, with a maximum deviation around 0.03 inches. 7075 T6 showed more elongation than 6061 T6, meaning it thinned more during forming. However, Both stayed below the 12% max elongation limit, so no overstretching occurred. Tensile testing results were inconclusive due to high variability. Since there's no standard method for testing bent corners, the data wasn't fully reliable. Future work should develop a more consistent testing approach for these regions. Hardness increased after forming due to strain hardening. While this improves strength, it can also raise the risk of cracking. Based on the prototype runs at Rollform Solutions, test results, and recommendations from industry contacts, rolls were designed to optimize the process for production scale. 19 passes were used in the production scale simulation, which allowed for reduced bend angles per pass. The additional passes resulted in reduced stress and strain in the formed part. Based on the test results and simulations, the team has developed the following guidelines for roll forming high-strength aluminum. It is recommended to reduce bend angles per pass by adding more passes. More roll passes can help to mitigate cracking, residual stresses, and longitudinal bow. The recommended minimum number of stations for 6061 T6 is 13, and for 7075 T6, 14. To achieve a 90-degree angle, it is recommended to overbend 6061 T6 by approximately 5 degrees, and 7075 T6 by approximately 9 degrees. For bend radii, we suggest using a radius at least one material thickness larger than the recommended bend radius. Finally, heat treatment methods should be investigated to improve the formability of high-strength aluminum alloys. The team faced several obstacles throughout the project. With only 7 stations available within budget, the tooling had to accommodate large bend angles per station. Large bend angles increased stress in the material, making it more prone to failure, such as cracking. Due to a lack of established literature on roll-forming high-strength aluminum, the team had to carefully design bend radii, offsets, and reliefs based on industry input and research into material behavior. Sourcing small quantities of 6000 and 7000 series aluminum also proved challenging. Finally, unexpectedly long lead times for materials created scheduling challenges and delayed key milestones. Special thanks to Steve and Travis at Rollform Solutions for assisting the team throughout the project, as well as providing tooling and equipment for the prototype tests. Thank you to Carl at Data M for taking the time to train the team in the Copra software, as well as provide insights into roll design. Thanks also to Arvind Srilatha at Katayama Manufacturing for providing additional project support.